things. And so I introduced the idea of if you've got an infinite series, it goes on forever and ever and ever, and you decide to cut it off right here, that's okay. It's going to be an approximation. But the question becomes, how bad is the error? How big or how small is the error? And is that okay? And this alternating series remainder was kind of our first look at that. We'll revisit it here in a second after Drew's question.
Yeah, so real quick, so for the alternating series, it has to be -1 to the something, right? Or it
could be a version of that, like it could be like -4 to the something, because you could always like split the -1 out of that.
So we did the one example that was -2.
Yeah.
Why didn't we just keep it at -2?
We could have. I think though that it's easier to essentially get the alternating part out, which is the -1 to the maybe n or n+1 or whatever. Get that out of there, because then whether the series converges or diverges depends on all the other stuff.
Okay.
And so if we separate that out, then we have a better basis for saying, and the other stuff says this.
Okay.
Full well knowing that it is an alternating series because of, for that reason. Okay, so with an alternating series, and by the way, full disclosure here, we will look at two different error bounds in this class, the alternating series error bound being one of them. We'll look at another one a little bit later. So the alternating series error bound is actually fairly simplistic. I'll highlight this again. If you have an alternating series that converges, then the absolute value of the remainder is less than or equal to the first term that you neglected. And at the end of the class yesterday, we talked a little bit about why that is, about how the plus-minus action continually reduces the error. So the biggest the error could be would be the first neglected term. So I thought we would do this example here. I think I can fit this all in one page. So let me scroll down just a little bit here, and we can do this all in one shot. So take a look here at our example here. Yeah, there we go. So number one, let's do the whole thing here. This is a good way to tie together this whole alternating series as well as the error bound. So you get this series right here, -1 to the n+1 times 1 over n factorial. So question A says, does this series converge or diverge? So what are some of the elements of things that you'd need to show in order to prove whatever it is you're about to say?
It's alternating.
Yeah, you got to identify it as an alternating series. So what tells you that it's alternating?
The -1.
Yeah, -1 to the n+1. So this right here tells us that it is an alternating series. So we say something like that. The series is alternating. You can just declare it because you can see that -1 to the n. The series is alternating. And then what about the rest? And this is kind of what Drew was getting at a second ago. What about that? What's going to be the behavior of 1 over n factorial?
Well, it converges equals 0.
Yeah, decreasing towards 0, right? So if you were to show that limit, you'd say limit as n goes to infinity of 1 over n factorial. N factorial grows extremely fast, so the denominator is going to get really huge really fast. Whether it gets huge, fast, or slow, it doesn't really matter. The top's going to be held constant at 1. So you will get 0 there. So then you can use the kind of that magical phrase to say you've seen the pattern that the series decreases in absolute value to 0. That's what I'm saying, decreases, right? Decreases consistently in absolute value to 0. Therefore, the series does what? Converges. Okay, so those are your conditions. You got to have an alternating series, and it's got to decrease. The terms have to decrease in absolute value to 0, and that shows convergence. Okay, so let's approximate the partial sum S5. So when n equals 5, we'll just list these out too. We're going to get some crazy fractions. Let's not get too concerned about actually adding them all up. I'm sure you could, but let's not.
Can we use our calculator?
If you're curious about it, that's fine.
Wait, what do you mean? Are we not listening?
Sorry?
No.
Okay. So when n is 1, our first term would be what? Actually, it would just be +1, wouldn't it? All right. When n is 2.
That's a little bit more difficult.
A little more. Well, so is it going to be positive or negative?
Negative.
It's going to be negative. And 2 factorial is 2, so yeah, I agree with you on the 1/2. All right, when n is 3, it'll be back to being positive. 1/6. 3 factorial is 6. When n is 4, we're back to negative. You can see that alternating pattern coming, into shape here.
24.
24, right? Yep. So 1/24. So that's when n equals 4. So we want when n equals 5 to get to that last term. 120? I agree. Okay, so if we were to, use a calculator, it really wouldn't be that hard. The common denominator is 120. We could get these added up pretty quickly, with or without a calculator. We'll just leave it like that for now. Says in part C says use the alternating series remainder for S5 to find the maximum error if using S5 to approximate the actual sum of the series. So if we use this partial sum and say, hey, this is an approximation, and what would the error be? So you can note this in a couple different ways. Here's one way. You can say the actual sum minus the partial sum. That would give us our error, right? So the actual sum minus the partial sum has to be less than or equal to what?
Wait, 1/6.
Yeah, so this is an alternating converging series. So it's just the next term, right? So what's the absolute value of the next term?
Wait, I'm still going. Times 2. 360 times 2, which is...
Drew, got it. I'm sorry, Hayden, he beat you. 1/720.
How'd you get that?
Say again? 6 times 120, yeah. Okay, so that tells us that the most of the error could possibly be is 1/720. Could be less than that, right? But that we know that is the biggest it could possibly be. So we ask ourselves the question, if we were doing something serious with this, is that acceptable? What if we decided that 1/720 was way too big of an error? What could we do to our approximation to reduce the error and make ourselves happier about that error?
Make the value on the...
Yeah, do more terms, right? What if we just added another 3 or 4 terms on there? Now the error is going to be a lot smaller. Is this your mission today? Okay, fair enough. All right, so that's your one example for the moment of this question.
So, how did you get the 1/720?
So we used these 5 terms right here from n equals 1, 2, 3, 4, 5 to generate our partial sum. And so we know it's an alternating series. We can see that that's happening. And so with an alternating series, the error bound is determined by the absolute value of the first neglected term. So in other words, we cut the series off, right?
Yeah.
We cut it off after n equals 5. So, if we thought about the true series, there's a bunch more terms on the end, right?
Right.
So the error is going to be less than or equal to the first one that we left off.
Right, so,
So the next
the
term
next one is,
would have been, so if I get rid of my plus ... the next one would have been minus 1/720.
okay,
So the error will be less than or equal to the absolute value of that first neglected term. That was the first one we left off, so that's the biggest possible error.
okay, that makes sense.
Okay. Other questions? So the other error bound we'll look at later on is kind of like this. It's definitely different, but it's kind of like this. We'll get there when we get there, though. So last chance for questions. Okay, so let's remind ourselves what I mentioned last time about how the alternating series test, or let me just put it like this, the alternating harmonic series actually converged because the plus minus really helps the terms add up to be something closer and closer to the actual sum faster. And remember, the concept is how quickly do the terms end up towards 0? Well, the plus minus really aids in that, right? And so what we're going to look at here, this is actually a new topic for this year, but it's something I've taught every year because I think it's a good thing to think about, and that is the concept of absolute and conditional convergence. So I want you to think about it like this. The word conditional means that there are conditions attached to the convergence, right? So I don't know if you've ever heard, maybe you hear people brag. I know, that happens sometimes where people will brag about how good they are, maybe their dad is, or how their friend is, or whatever. oftentimes there's conditions put on it, right? So here's an example of a condition. Let's say that someone is down in the weight room and they are working out, they're trying to do squats and they're trying to like max out their squats, and they throw 3 plates on there, 315 pounds, going for it big time, right? They're really giving it a shot. They're going to go for their 1 rep max. They give it a shot. They got spotters, right, because they're smart. And they lift it, and they get all the way back up. They have good form and everything. We move with it, they don't realize is maybe their spotters helped them, right? Maybe their spotters lifted up on the bar just a little bit because they weren't getting it. They were trying really hard, but they weren't getting it. So we could say that this person could squat 315 pounds on the condition that they get a little bit of help. That make sense? Agreed. Yeah, agreed.
Just like watching the Harry Potter movies without moving.
I feel like you mumble the most interesting things. And it's just like mumbling.
It wasn't about Harry Potter. It was towards Will.
Oh, okay. That's why you were mumbling. And so, to Hayden's point though, that could be a pretty important condition, right? You can say, well, hey, you got help. You didn't really do it, right? Here's some other conditions. Like somebody might say, hey, you know what? Those of you that ski or snowboard, somebody might say, man, I'm a really great skier, a really great snowboarder, and come to find out that they can really only ski on like perfectly groomed, smooth runs. You throw them in some powder, throw them in some bumps, and they can't get down enough, right? So their skills as a skier are very conditioned on the condition of the ski slopes, right? Does that make sense? And so conditional convergence is a pretty strong thing to say. What that means is the series might not be able to converge if it doesn't get some help, kind of like the person trying to squat 315 pounds. The series might need a little bit of help. What do you think could provide some help to a series?
Alternating series.
Yeah, the alternating element could provide a lot of help. And so, he is on it, yeah. Hayden, I don't know. I don't know if this needs to turn into some kind of math battle. But if it's going that way, he's doing well. Standpoint, I think part of the battle should be focus. If you lose focus, I think you both lose. So, what we're going to basically do here is say, hey, we get it, the alternating element helps you, but what if we took it away, would you still converge? Right? So, person who's trying to squat 315 pounds, if we took away your spotters, could you still do it? Skier on the ski slopes, hey, if we threw you out there in some ungroomed powder or just some crusty, nasty stuff, could you still ski well? If we take away your advantage, could you still do it? That's what we're going to question here, right? If we take away the alternating element, do you still converge? So the little note here says sometimes a series will have positive, negative terms, but maybe it won't be an exact alternating series, or maybe it will be an alternating series. At times we will test, we'll be asked to decide, does this series really need the alternating element? Some series don't need it, some do. Okay, and we're going to test that out here. So absolute convergence test is this right here. If the series sigma of absolute value of a sub n converges, then the series a sub n converges. What does the absolute value do to the terms?
Makes them all positive.
Yeah, it takes away the alternating element. So it might have been plus minus plus minus. Well, the absolute value just makes them all plus. Okay, so if you think about this, if you take away all of the plus minuses and all you have are pluses, then that's a pretty strong statement, right? That's saying that the series doesn't even really need those plus minuses to converge. And so you would say that that series is absolutely convergent. Whether it gets the plus minuses or not, it will converge. Conditional convergence, a little bit different. We would say this right here. The series is conditionally convergent if sigma an converges, but sigma absolute value of a sub n diverges. So in other words, if you take away the plus minuses, and that causes the series to diverge, then it's conditionally convergent, right? It converges based on one condition, that it gets its pluses and minuses. If you take them away, it diverges. That means it's only conditionally convergent. You see what I'm getting at? Does that make sense? Do you have any questions? We're going to practice it here in a second, but yeah. Questions or thoughts? Okay, well, let's try this out. We get to make hopefully some interesting judgments here. So the instructions for all of these, I think there's 6 or 7 examples. It says determine whether each series is convergent or divergent, and then classify any convergent series with absolute convergence or conditional convergence. Okay, so in other words, will the plus minuses be necessary or are they unnecessary? We'll make that judgment on absolute or conditional. So take a look at number 1. It says sigma from n equals 1 to infinity of sine of n over n squared. Let's see, I need to scroll just a little bit here. Any plus minus stuff going on. How do you know it'll have plus minus stuff going on? Sine, right? Sine has positive and negative terms. Of course, we don't know if it's going to be exactly plus minus, right? Let's do a couple of terms. Just use your calculators. What's sine of 1? Just throw it out there. Use your calculators. Let's just try to get a sense of the pattern. We know that the bottom is going to be positive because it's n squared, but sine of 1, sine of 2, sine of 3. Let's get some kind of a sense of whether we have pluses or minuses. Maybe. So sine of 1 is? So positive 0.841. How about sine of 2? That would be our next term.
It's gonna change at 3.14.
Okay, so positive, right? How about sine of 3?
Still gonna be positive.
Oh, 3 positives in a row.
But 4, no.
Sine of 4?
No.
Negative. Man, Hayden, I don't know. Hayden's on it right now. How about sine of 5? I bet you that's negative, correct? Sine of 6 is negative. So we had 3 positives, 3 negatives, and I bet you once you get to sine of 7, you have to be in positive. Now somewhere in there we're going to get a little overlap, and that may be perfect, like 3, 3, 3, 3. That'll get a little bit messed up eventually. But the point is that there are some positive terms, there are some negative terms, and so we want to consider this whole conditional or absolute convergence thing. But I think what we want to do here first is, decide, okay, this is not exactly an alternating series. It's got some pluses and some minuses. As it stands right now, including the pluses and minuses, will it converge, and how do you know? What would you use? Let's go all the way back to the beginning. What does the nth term test tell us about this series? Right, but so what does it specifically tell us about this? Say again? An nth term test will never tell you convergence. Nth term test. Does the nth term test go to 0 or not?
Yes.
It does, which tells us the nth term test tells us nothing. Okay, so nth term test is silent. Is this a geometric series?
No.
How do you know?
Because
Because what?
No n is an exponent.
Yeah, no variable exponent on a numerical base, not geometric. How about, what do we do next? Like an integral test. Think the integral test is going to be helpful?
It's not always positive, so you can't do it.
Yeah, you're right. Yeah, it's not positive the whole time. Even if it was sine of n over n squared, that's an ugly
Yeah, I don't know if I could do that.
integrand. We might be able to use integration by parts, but probably not.
No, or it's not.
Because of that negative exponent. It's not going to go well. Is it a p-series?
No.
Why not? Sine of n. Yep, not a p-series. Gosh, what are we left with?
Nothing.
Yes, we are. We've got
Comparison.
some kind of a comparison. Yeah, we could definitely do a comparison here. What could we compare this to? 1 over n squared, I think, would be pretty wise.
But it, like,
Why did you pick that, Jared?
Because we know that since it's alternating, it's going to be less than that.
Right, and what's the highest that sine of n could conceivably ever be? 1, right? So no matter what we get out of sine of n, it could never be higher than 1, right? It's always going to be 1 or lower. Yeah. So we could compare it. I think that's a wise move. So let's do that. Let's say 1 over n squared. How does that relate? That's always going to be greater, right? It's going to be greater than or equal to. Yep. So let me rewrite that just a little bit. Let's put it like this. 1 over n squared and sine of n over n squared and 0. Okay, so sine of n over n squared is always going to be less than or equal to 1 over n squared.
But that's not always greater than 0.
Yeah. Sorry, I kind of skipped over this. Let's talk about this now. Let's do this. I think this will be the best time to do it. Okay, let's talk about it like this. With this series right here, it is technically not alternating, but we get a lot of the plus minus stuff, right? 3 minuses and a plus, 3 minuses and a plus. You can actually rearrange it a little bit. We could say, I think at this point, converge. I'll put a question mark. It seems like maybe it will, but I think there's a pretty serious question mark. So what I would go for is this. I would go back to what we saw earlier on the page. If I take away all the minuses and I make everything pluses, if it still converges, then wouldn't the original series converge as well?
Yeah, so we're doing it.
Okay, so what I think I'm going to do is I'm going to put this in absolute values. Let's do it like that. So that guarantees the positivity, right? Okay. And it's the comparison still holds because anything that was negative, the lowest it would have been is -1. So it still fits within that comparison. So then we could say, based on that comparison, on our interval 1 to infinity, let's see here, 1 over n squared
It's a P series.
does what?
It converges because it's a P series.
Because of the what?
It's a P series.
P-test, yep. So P-test, therefore, we can say that our original series, in absolute values, also converges. What would be the overall reasoning there? Comparison. And here's where we can make our broad answer. So we can bring it back up here and say, therefore, what is true about the original series? It absolutely converges, right? Yeah, therefore that series absolutely converges because, to just use plain language, what we did is we took away all the pluses and the minuses and made them all pluses, and it still converged, right? So if we give it back some of the minuses, whatever terms were minus, then it's got to converge even more strongly. It's an even stronger argument that it would converge. Okay.
Does P stand for anything? Or is it just
Power?
Oh.
Yep. Yeah, it's not a random letter, although sometimes it seems like it's just randomly chosen. This one, P for power. Yeah. Good question. Okay, so number 2. Let's take a look at this one. Let's just look at this as it stands at the beginning here. Number 2 is definitely alternating, right? You can see that alternating element at the top. It's going to cause the terms to go, plus, minus, plus, minus, plus, minus, dot, dot, dot. So let's just think of this simply as an alternating series here at the start, and then we'll deal with that absolute conditional thing at the end. So what do you guys see? We can declare this to be an alternating series.
I'm going to say, I'm calling it right now, it's conditionally convergent.
Okay. So let's deal with this. As an alternating series, then are you saying that it converges or not?
It converges as an alternating series.
Okay.
But we take
Because why?
on the limit as n goes to infinity of 1 over n, it's 0.
Yep, so if you remove the alternating element, you just consider the other part, you do get 0 as n goes to infinity. And you can see that as n grows from 1 to 2 to 3 to 4 to 5, the terms will successively, continually just decrease, right? So we can use, again, kind of the magic phrase, the terms will decrease in absolute value to 0. And because it is an alternating series, we can say, therefore, the series converges. But we were asked to decide, well, what about the whole conditional absolute thing? So if we want to test out that, what do we need to do? What do we need to take away? Yeah, the negative stuff, right? All the negatives. How do we take that away?
Just make it one.
Say again?
Just make it one on
Right, but what are we actually doing?
top. Multiplying it by net.
Ooh, definitely not.
Absolute value.
Absolute value. So I'm going to go sigma from n equals 1 to infinity of absolute value of negative 1 to the n plus 1 over n. Of course, what that does effectively is takes away all the negative signs, right? Every other sign won't be negative now. So we can imagine this now, and this is kind of what Hayden was getting at. I think we can imagine this as sigma from n equals 1 to infinity of just 1 over n. That's essentially what it would become. So what about this series then? Does that series converge or diverge? Yeah. So we can say that series that we just described right there diverges because it is harmonic. What other reason could you have given? Or? Say again? No such thing. Integral test. I don't know what you mean by limit test. A lot of them have limits. Oh, nth term test. Well, but the nth term test goes to 0, right?
I was talking about the integral test.
The integral test. Oh, because limit is b goes to infinity integral. Okay, got it. All right, so if we take away the pluses and the minuses, it loses its convergence, right? And so that means it's conditionally convergent, right? It needs the pluses and minuses. So we could say overall, therefore, sigma from 1 to infinity of the original series here is conditionally convergent. I really see this type of thing set up on a multiple choice, possibly free response, but I think it's most likely a multiple choice scenario, would be my guess. Okay, got a few more to do here. You guys good? All right. So Hayden, your guess at the start was right on the money.
I know.
Nice job. You don't hit Jasper?
Jasper, I have faith in you.
All right, so looking for, is this convergent, divergent? If it's convergent, let's decide if it's conditionally or absolute. Doing number 3. What'd you guys decide? Convergent or divergent? Yeah, this thing just diverges, whether it gets the plus minuses or not. So let's think about how you could get there. It's definitely alternating, right? It's negative 1 to the n is going to give you that, I guess it'd be plus minus, plus minus, plus minus, right? You're getting the alternating series thing going on. But in order for the alternating series to converge, we need the terms decreasing in absolute value to 0. What did you find there? Yeah, increases towards what? Infinity, actually, yeah. So you might say, hey, the series is alternating. Maybe you started off with that. You definitely want to identify it as an alternating series, especially if we're headed for convergence. But then you'd say the limit as n goes to infinity of the other parts are going to give us kind of a disappointing story. N factorial over 2 to the n. How did you guys evaluate that limit? What did you think about? Yeah, the rankings thing, right? So n factorial will eventually get infinitely steeper than 2 to the n. And so, yeah, infinity here, which importantly does not equal what? 0. So we can say, therefore, the series diverges. And what would be the reason there? Nth term, yeah. Remember the alternating series test will kind of dodge out of its responsibility of saying that the series diverges, and it's really the nth term test here that does our job. Okay. Questions? Okay.
Term test, you have to be positive,
I think you're thinking about the integral test again.
so it doesn't matter.
I just tested the non-alternating part anyways. I just tested out the...
Yeah.
So, Hayden, if you want to think about it like this, the graph of that series would definitely alternate, but here's what it would do. It would start off here, then here, then here, and it would just be, that's probably not even, this last one's probably not good enough. It would just continue to widen out. It would get further and further from the x-axis as opposed to getting closer and closer to it. Okay, number 4, I realize might cause some serious grief. Check out that numerator. -1 to the n times n plus 1 over 2.
But it doesn't really matter because it's just.
It's only going to create an alternating element. That's it. That whole numerator, if you think about it, when n is 1, what's the top going to be?
-1 or 1.
I think, well, let's see here. It would be 1 plus 1 is 2, over 2 is 1, times 1 is 1. So I think the whole top would just be -1 when n is 1. When n is 2, it'd be 2 plus 1 is 3, then the 2 in the front and the 2 on the bottom would cancel out. So I guess we would get 3 there, so it'd be -1 again, wouldn't it? Let's keep going. I don't know. So that was when n is 2. When n is 3, it'd be 3 plus 1 is 4, over 2 is 2, times 3 is 6. So there would be a positive 1. That makes sense? So you're going to get some minuses and some pluses, right, depending on where you're at. So I think our best bet here would be to do an absolute convergence test right away. Let's take away the minuses and the pluses and make them all pluses, and let's see what happens. So if we go sigma from n equals 1 to infinity, and we put this in absolute value, I won't do that. Put the whole thing in absolute value, in all of its glory.
That means you have an R of 1/3, so you're going to.
That would essentially give us, when we take away all the alternating stuff, it would essentially give us this, right?
Which is.
Okay, so will that series, 1 over 3 to the n, converge or diverge? Reasoning? What? Say it again? GST. Yep. Now, technically, you could think of it as 1/3 in total to the n. So you'd say this converges because r equals 1/3 using the geometric series test. Say again?
Which is less than 1.
R equals 1/3, which is less than 1. Yep. Thank you. So we got our geometric series test settled in there. And so since we took away all the minuses and had only pluses, we still got convergence. So what can we say about the original series? It is absolutely convergent, right? Whether the plus minuses are there or not. So we can say that series is absolutely convergent. I'm sorry, can you say it one more time?
Should you state if this is an alternating series?
I don't think it is, though. Unless I messed up my arithmetic, which happens from time to time.
Is alternating only when one has a one?
Yeah, technically alternating. Although technically you can do, there's some crazy stuff you can do with alternating series. You can rearrange them to do all kinds of stuff you would not expect. And so even if you had like minus, minus, plus, plus, you could rearrange it and be minus, plus, minus, plus. So, but in its original form, no. Yeah. Okay. Other questions? Guess still got a little gas in the tank?
So have you found that after doing the absolute value part, that, like, let's say it was just like 3n, and so it would diverge,
Mm-hmm.
would you be able to say anything?
Well, you'd have to go back and analyze it a little bit more and say, okay, if I got the minuses and pluses back in there, what happens then? But if it was just 3 to the n, like you said, that's going to be an nth term test, right? Whether the minuses and pluses are there or not, you're going to get a diverging series.
Yeah.
So, in that specific case, you could make that conclusion. No, I didn't really compare anything. I took away the minuses and pluses with my absolute values.
So is that not?
That's not really a comparison. What we're essentially doing there is we're acknowledging that the fact that there are some terms that are negative helps the potential convergence, right? So if we take away that help and it still converges, then we can say, well, with that help, it definitely converges. So it's not really a comparison, it's just a removal of the sign changes and then making a judgment based on that. Okay. All right, we got time for one more, maybe two more. We'll see how it goes. Definitely think you can do number 5. I'm sure you could do number 6 as well. So feel free to do one or both. With a couple minutes left, we'll at least discuss number 5. With number 5, do you see in number 5 the classic alternating element right there? Negative 1 to the n, it's just going to go minus plus, minus plus, minus plus forever, right? And so I think what we can do is we can discuss that, and we say, the series is alternating, and that will cause us to think in a certain way. So if this series is alternating, then we want to look and ask ourselves, do the terms decrease in absolute value to 0? So in other words, as n goes from 1 to 2 to 3 to 4 to 5, do the terms decrease and do they head towards 0? So do you guys see the decreasing pattern? Right, so n goes 1, 2, 3, 4, 5, the overall value of that term is going to drop. But is it heading towards 0? We could say limit as n goes to infinity of 1 over root n. Well, it's going to happen pretty slowly, but it's going to happen, isn't it? We're going to be heading towards 0. So we can actually say this, because the series is alternating, the terms in this series decrease in absolute value to 0. Therefore, what's our conclusion about this alternating series? Converges, yes. Therefore, the series converges. But then the question was posed at the start, well, if it's converging, then what if we take away all the sign changes? Then what happens? So if I consider that, it would look like this. Sigma from n equals 1 to infinity in absolute values, negative 1 to the n over root n, which is effectively then sigma from 1 to infinity of 1 over root n. So what judgment can you make about that series? Diverges because? P-test. There you go. So that series diverges because P equals 1/2, which is less than or equal to 1. So P-test. Okay, so now we took away the minuses and the pluses and made them all pluses, and that took us away from convergence and made it diverge. So what's our final conclusion? That's right. Therefore, this series in its original form is conditionally convergent. All right, so when I see you all on Friday, we'll try to clean this up with number 6 and move on into 9.6. Have a great day. Test your question.